In this course, we're going to set up connectivity between two PCs that goes through a router. To begin with, connect to the router and set up IP address 192.168.1.254 with a mask of 3 times 255.0 on its fast Ethernet 00 interface and IP 2.254 for the 01 interface. Make sure to properly mount the interfaces with the command no shutdown. So now we have the network 192.168.1.0/24 on the left, and the network 192.168.2.0/24 on the right. If you launch the ipconfig command of the PCA, you can see that it carries IP11, and that the default gateway is the IP of the router's 00 interface. On the PCB side, this is the IP22, with the default gateway to the 0/1 interface of the same router. Now if we launch the show IP route command on the router, we can see our two networks, the 10 and the 20, which are directly connected to it. Let's say PCA wants to communicate with the PCB. First, it will prepare an IP package for the 192.168.2.2. As PCA realizes that this IP is not part of its own network, then it sends it directly to its default gateway, that is, address 192.168.1.254, which corresponds to the router's 0/0 interface. When the router receives the package, it checks the destination IP address and analyzes its routing table. As IP 192.168.2.2 corresponds well to the 192.168.2.0/24 network, the router transmits the packet directly to its 0/1 interface, and the PCB receives the IP packet that was intended for it. Now that we've seen how a router works, we'll look at its configuration, and mainly on the router on a stick method, that is to say, with sub-interfaces. On this diagram, we have a switch, on which is connected PCs that are part of two different VLN, the VLAN 10, and the 20. And on the right is a router that is connected to our switch with a single cable. The router must have access to both VLAN networks so that it can do its routing job. In other words, it must have one interface that is part of the network. 192.168.1.0.0, which is the VLAN 10, and one second interface in the network 192.168.2.0.0 of VLAN 20. In order to avoid buying a second interface, we will instead create sub-interfaces on the router. These are virtual interfaces in which we can set up an IP address for each sub-interface. To name them, you can choose any number, but it is still better to use the A number of VLAN to better navigate in cases of troubleshooting. A sub-interface of 0.10 for the VLAN 10 and 0.20 for the VLAN 20. Now let's see how configured they are. We'll start by mounting the physical interface 00 of the router by making a no shut. Then we will go into the configuration mode of the sub-interface 0.10. The encapsulation .1q command plus the number of the VLAN is very important because it allows showing the router which VLAN belongs to this interface. And the IP address affects an IP that is part of the same network as the VLAN 10 on the virtual interface. Here we choose the last IP usable, the 254. This IP will therefore be our default gateway for all PCs of the VLAN 10. And we're doing the same under interface 020. And 010 belongs to VLAN 10 and 020 to VLAN 20. And finally, we'll go and see what's going on in the routing table with the show_IP_route command. We can see our two sub-interfaces being part of the two sub-networks. This allows the router to route between the two VLAN. That is, the VLAN 10 PCs can communicate with those of the VLAN 20 through the router, provided, of course, that their gateways are properly configured. Now we will talk about static routing. Here we have two routers. The A router with two fast Ethernet interfaces, the 0/0 and the 0/1. The 1/1/1/0 network was configured on the 0/0 port, and the 5/5/5/0 network is on the side of the 0/1 interface. The B router also has two fast Ethernet interfaces. The 2/2/2/0 network is on the side of the 0/0 port, and we find the same network as the router A, the 5/5 interface 0/1. The 1 on the A router side means that Ethernet interface 0/1 carries IP 5551. And the 2 on the router B side matches IP 5552. Unlike a switch, on a router, a single IP address is set up on each interface, and every interface in the same router has to belong to different networks. On the other hand, at the other end of each interface, there must be the same network. Here, each router contains in its routing table two entries. These are the networks that are directly connected to it. If you look closely at the routing table, router A has no knowledge of the 2/2/2/0 network, 2/2/0 network that lies behind router B. And conversely, the B router does not know the network that is at the other end, the 1/1/1/0. So how do you get the two routers to know about these two networks? Well, there are two ways to get them to learn, either by static routing or by dynamic routing. If you use static routing, you'll have to do it all on your own. That is, it's up to you to tell the router where to send IP packages for this or that network. So it can be fun at first, but it still takes a lot of work. And a good computer scientist is a lazy computer scientist, which means that he prefers to automate his tasks. A dynamic routing means we use a routing protocol that will exchange network information between routers. Let's start by seeing the static road configuration. Without router A cannot reach the 2/2/2/0 network that is at the other end. Let's say our routers are out of the factory. We're going to set them up completely. First, connect router A and access in global configuration mode. Then, set up IP address 5551 on the 01 interface and the address 111.254 on the 00 interface. Don't forget to do a no-shut to mount the interfaces. And I also set up the IPs on the B router side. Before setting up our static route, we're going to go and look at the routing tables of the two routers, doing a show IP route. By default, a router only knows its networks that are directly connected to it. That's why router A only sees network 5550 and 1110. Router B also sees the 5550 and sees the 2220 network. At the moment, router A has no idea to join the network 2220/24 because there is no entry in its routing table. That's why we're going to create a static route that tells router A how to reach the network behind router B. The iproute command creates a static route. Network 2220 is the network we want to reach from router A. The address 3 times 2550 is the subnetwork mask of the network you want to reach, and the address 5552 is what is called the IP address of the next jump. This is basically where we want to send traffic. So basically, I tell router A that as soon as it receives frames for network 2220, then I transfer them to the 0/1 DOE of router B. And since this network is directly connected to it, there will be no problem. Finally, we're going to go back to our router A routing table. Here, the showIProute command shows us, well, this time an entry for the network 2220/24. And if we want to build the way back, that is, router B can join the network behind router A, we should launch the command on route B, iproute 1110/255/255/255/051. And that way, the PCs on the left can communicate without problems with those on the right. Every time an IP package arrives on a router, it checks its routing table to see if it knows the destination network. If so, it will transmit the IP package, and if it has no idea, then the package will be deleted. We can also say that the package will be dropped. As you've seen, static routing is very simple to set up, but it has many drawbacks. For example, in this topology, there are many routers, and therefore also a lot of networks. If I want all of these routers to be able to communicate with each other, I'm going to have to set up a lot of static roads. And if one of the links falls, I should change my routes manually so that my traffic can take a new path. That's why this topology would be suitable for a dynamic routing. With a dynamic routing protocol, information from all networks is constantly flowing between routers. The advantage is that if a link falls between two routers, then it will update automatically to find a new path. There are different types of routing protocols. On this topology, composed as a router, we have autonomous systems. This is what is represented in the cloud. Here we have the AS10 on the left and the AS20 on the right. An autonomous system is a set of routers that belong to a single administrative area. For example, your corporate network could be an autonomous system. Your internet service provider has its own network, which is also another autonomous system. Standalone system, the routing protocols that circulate are IGP type. OSPF and EIGRP routing protocols are internal routing protocols. Between the autonomous systems, there are external routing protocols, which are called EGP. In an EGP type, only one internet routing protocol is used. It is called BGP. For now, we will stay on the internal type, because the external routing protocols are not part of the CCNA. Here is a new topology, with a standalone system, in which several routers are included. The PC on the left is part of the network 192.168.1.0.0, with a mask in /24, and the right server is in the network 192.168.2.0.0. The PC on the left would like to reach the right server, and the question we could ask is, what path will it take with all its routers in the middle? Well, it depends on the routing protocol that we're going to use. Whether it's OSPF or EIGRP, they both have a different vision to determine the shortest route from source to destination. Both protocols determine the best path using so-called metrics. For example, OSPF uses cost as a metric. That is, it will examine the bandwidth of the interface to choose the fastest path. It would rather use 100 megalink than a 10 megalink. And EIGRP, which owns Cisco, uses several metrics. It will examine the bandwidth as well as interface delay. And if you want, you can even add the load and reliability of the interface as metrics. We'll see this in more detail in the courses devoted to OSPF and EIGRP. We just have to keep this in mind, that a metric allows the routing protocol to determine the shortest route to the destination. So in your opinion, can we use multiple routing protocols at the same time on a router? The answer is yes, and it even happens very often, especially when a company merges their networks with another. To return to our topology, the autonomous system uses two routing protocols, EIGRP and OSPF. The EIGRP protocol states that the router must send the IP packages using the path at the top, and OSPF tells us that the router must send the packages using the bottom path. All this is good, but will our IP packages go up or down, or on both paths? When two routing protocols provide information on the same decision network, the router must make a choice. You cannot use one EIGRP move and both after OSPF. The router will make that decision thanks to the administrative distance. The lower the administrative distance, the better. As you can see, a road directly connected is at an administrative distance of 0. This is normal since it is directly connected to the router, so that is the most reliable thing. A static road has an administrative distance of 1. As this is something we manually set up, the router will prefer to use a static route than any dynamic routing protocol. The EIGRP protocol has an administrative distance of 90, and OSPF of 90, and OSPF is 110. Which means in our example that the packages will go through the top. After, if EIGRP is more reliable than OSPF, it's mostly because it owns Cisco. We just have to see the three classes of an internal routing system. In the next lessons, we will go into detail about the different classes. At this point, you just need to know which class these three protocols belong to. RIP is a remote vector routing protocol. EIGRP2, except that it's an improved version. And OSPF